In the United States, there are over 49,000 bicyclist motorist crashes and over 700 bicyclist fatalities every year. The motorist fails to see the bicyclist in a large fraction of these accidents. In this project, a smart instrumented bicycle with sensors is developed in order to prevent car-bicycle collisions. The sensor system monitors nearby vehicles and predicts danger of a collision. If there is a danger, an audio warning is provided to alert the car driver about the presence of the bicycle. The research challenges in this project come from significant cost, size, weight, and power consumption constraints on a bicycle. The sensors used on autonomous driving cars are too expensive for a bicycle and too difficult to power using batteries on a bicycle. The sensors on the bicycle will address the following three types of crashes. In this video, I will talk only about the rear collision prevention system. A single beam laser sensor is implemented on a rotating platform for rear collision prevention system. The laser sensor is very inexpensive and it can measure distances up to 40 meters. However, the sensor has low sampling frequency and it has only a single laser beam. Let's look at the simulation using open loop scanning with the laser sensor. Due to the low sampling frequency, we only get occasional readings with the laser sensor. So instead of doing open loop scanning, an active sensor orientation control algorithm is proposed. What we try to do is to try to track the right corner of the car so that we get both longitudinal and lateral distances to the car. For the tracking, the orientation of the sensor is controlled in real time using receding horizon optimization. For the vehicle motion estimation, an interactive multiple model estimator is utilized. Let's look at the simulations using the active sensing algorithm. Initially, the sensor system conducts open loop scanning. After detection of the car, it tracks the right corner of the car continuously. Here is an experimental video using active sensing algorithm, and you can see how the sensor tracks the car. Here is another experimental video in which the car turns towards the bicycle and warning is provided. We also developed a new hybrid observer design technique for non-monotonic nonlinear systems, and we utilize the observer design technique for vehicle motion tracking applications. The nonlinear observer for vehicle motion tracking application is experimentally evaluated by using a radar sensor. We have now a new generation bicycle which is an e-bike, and we are doing a field operational test with that bicycle. The new generation bicycle has a more customized warning sound based on a human factors study that was done by our collaborators Dr. Nicole Morris and Professor Max Donas. We have a number of bicyclists who are participating in the field operational test. We are collecting all the test data from the bicyclists and will evaluate the system from this real-world data. I would like to thank my advisor Professor Rajamani, Human Factors Study Team, Professor Donas and Dr. Morris, and my research team, Lee and Jemming. This research was supported by the Road Safety Institute and the National Science Foundation.